So welcome to the Illinois EPA Office of Energy's spring webinar series and our session today, uncovering energy efficiency opportunities for Illinois water treatment plants. This is one of the final events in our spring series, but we'll have more in the fall. So stay tuned. We'll keep you on our outreach list. I see everybody is saying hello in the chat. Please take a moment to say hi and tell us where you're from. It's great to have you all here this morning. So in this session today, we'll provide an overview of the common energy efficiency savings measures we've identified through our energy assessments provided by the Illinois EPA Public Water Infrastructure Energy Efficiency Program. We'll also cover topics such as investigating VFD potential, optimizing filters to minimize water waste, and simple building upgrades to minimize your energy consumption. So we'll also talk a little bit about some opportunities to connect to available incentives and funding opportunities to implement energy savings measures and equipment at your plants. So we're really excited to have you here today and to join us. So we will record this session and we'll share the recording as well as the slides after the session has been completed. This webinar also counts for 1 hour of CEUs for water treatment operators, and we'll share the course number and certificates with all participants once they're available. Illinois EPA is still entering our course into their system, so we will send them as soon as we possibly can. Finally, if you have any questions throughout today's presentations, please either pop them in the chat and I'll keep track of them for our discussion at the end of our webinar, or save them until the end of the webinar. We will give you an opportunity to actually unmute and ask your question live if you want. So either pop them in the chat or wait till the end for questions. I'll also be popping some prompts in the chat as well. So please feel free to use the chat to communicate with us as well as others in the webinar today. All right, so thank you for being here, Sean. We'll move to the next slide. Just wanted to tell you a little bit about CDAC, the Smart Energy Design Assistance Center, before we get rolling today. So we are a applied program here, research program here at the University of Illinois in Urbana-Champaign, working in collaboration with the Illinois EPA, Office of Energy, and Illinois Sustainable Technology Center to offer or to help buildings, any customers, reduce their energy footprint. So we really want to help you reduce, save money, achieve energy efficiency, and overall help your buildings become more sustainable. And again, just to note, our program is sponsored by the Illinois State Energy Office, so we thank them for their continual support of making this program and what we do possible today and beyond. So I just want to jump into a little bit of a program overview for you about what do we do under this Public Water Infrastructure Program. So they partnered with us and the Illinois Sustainable Technology Center at the Illinois EPA Office of Energy to help local municipalities reduce the cost of water and wastewater treatment. So luckily, within the last year or so, we've been able to start serving water treatment plants. So we're really excited to work with you in your facilities to help you identify energy savings opportunities or help you get these projects done. One of our core components of the program is no-cost energy assessments for your water treatment facility. So usually similar assessments cost between about $6,000 to $12,000, but through the department, or through the Illinois EPA Office of Energy, we're able to provide them at no cost to you. So in these assessments, we really look at your overall plant function, your buildings, and try to find opportunities for efficiency. We build a comprehensive report that lists costs of upgrades, estimated payback periods, and any applicable incentives and funding opportunities that can help your plant implement our recommendations. So a little bit about the process. How do you get started in an assessment? First, there's an initial pre-qualification, and it's pretty easy to get pre-qualified. If you're located in Illinois, if you're willing to have us come on site, share some facility information. We do request things like utility data and just a little overview of your plant before we come on site. If you're willing to share the final assessment report with the Office of Energy, not a regulating body, but if you're willing to share the assessment report with them and you're publicly owned, you qualify for an assessment. Like I said, fairly simple, quick conversation with myself or another one of my team members to get you started. The next step of the assessment process is the data collection. And this is really the primary meat of what you will be working with us as an operator on. So you'll provide some basic facility information to us, and then some energy use data, monthly operating reports to understand your flow or your pumping usage of your water, and process information. So that's really your role in this, so we take care of the rest. And we're happy to assist collecting that information as well. That information gives us a really good baseline on what's happening at your plant before we come on site. So we can be more informed. We can share with you your energy baseline and benchmark, and also be ready to ask questions about your plant when we come for the on-site assessment. So once we get that data, we schedule a site visit with you and come out on site. And really what we do in that site assessment is we probably 1 week before or after the site visit, you receive a short list of potential measures. And that's based on our site. So our site assessments take about 1 hour to 2 hours. We walk around from process start to process finish, take a lot of photos to help us really be able to write a great comprehensive report for you. And then we get to work. So we'll send that short list to you after the site assessment. About 1.5 months, 2 months after the site visit, you'll receive your final report, and then you have an opportunity to read that through and follow up with us for any questions or any interest in implementing anything that we've recommended. If you're interested and need support, we can also provide that too. So if you want to apply for incentives, or you want to learn more about folks that offer those types of services, we can totally help connect you with the resources to get those projects done. So we're really your partner in helping you find energy efficiency opportunities and get those opportunities completed at your plants. Illinois EPA will also follow up just to check and see how everything went, get feedback from you as a customer and of the site assessment, and just make a connection with you. They want to meet with you too. So site assessment or site visit is really simple. So again, before the site assessment begins on site, we have a pre-meeting. We talk about your benchmarking and we discuss known issues of at your plant, like equipment or process or energy use. We talk with you about your desired upgrades, and we talk through some questions we have about your process. And then during the assessment, as I said, we go from start to finish, or start of your process to the end of your process. We'll walk through that flow and we'll work with, and we'll talk to you about efficiency ideas or clarify anything in your process. Again, lots of photos. And then our team will wrap up with you and start the report development process. So why is it a good idea to do this energy assessment? One of the things that we find a lot, or we're finding a lot now, is that plants are really seeing an increase in energy costs at their facilities, like big rate hikes for clients, for utility clients. So we really want to take a look and see, well, how can you operate more efficiently? What are some equipment upgrades that'll help you operate more efficiently and reduce that energy cost for not only really for your plant and your municipality. We also really want to help identify process improvements. So not everything will be capital intensive. Some things will just be operational things that we see that we've seen at other plants that may work well, that may save you energy and money at your facility as well. We also really in our reports prioritize process equipment improvements that'll be really good for budgets and really good for your bottom line. So we actually do a payback period calculation for you. So it can help you prioritize things at your plant that you've been thinking about. It also, this report really helps convince committee members or board members or administration to invest in upgrades at your plant. It's an easy to read report, easy to digest, and it's a tool that many of our past assessed plants use to move projects forward. And we all know we want to help you move your projects forward. So anything we can do to support those efforts, we'll do that through this process. And then also, it helps really advertise that you as a water treatment facility, an entity for your municipality or your community, are taking steps to keep rates low for your customers and doing it in a sustainable manner. So there's a lot of benefits of conducting assessment, whether you're an older plant or a brand new plant, there's always efficiency opportunities, and it never hurts to take advantage of this no cost service. Also, one thing that's not on here, it prepares you for incentive funds and grant opportunities. So sometimes the incentive programs or grants require that you have an energy assessment before you apply for funds. So it's definitely a great time to get started with an assessment, get prepared, and have that ready for applying for incentives or grants. Not all of them do, some of them do. That's been a benefit that we've heard a lot of from our customers. And this here is what a sample report looks like. So here at the top right, you have a breakdown of your electricity use, and that's your benchmarking that we provide. And then the bottom table here really highlights an example of the different types of measures, and this is a summary page of all the measures we've identified, their kilowatts hour saved, therm saved, and then the potential cost, capital cost for the project, the payback period with or without incentives, and then just really that return on investment. So, it's a really great roadmap to help you plan and achieve energy reduction opportunities at your plant. So we are really excited to get to know you more. If you're interested in an assessment, I'll pop a link in the chat that you can fill out that just indicates that you're interested, and I'll probably be the one to give you a call and say, hey, let's talk about your plant more. And we look forward to working with you and helping you reduce energy at your facilities. Without further ado, I'm going to turn it over to my colleague, Sean. He's a senior energy engineer here at CDAC, and he's going to talk about, well, what kinds of measures are we seeing at water treatment facilities, and what kinds of things might we find at your plants? So Sean, I'll hand it over to you. Thank you.
Thank you very much, Cassie. I appreciate it. Well, one of the big things that we find at most wastewater plants is pumping energy. For most facilities, it's somewhere between 75 and 90% of your energy use is for getting the water out of the ground or out of a lake or out of a river, pumping it through your process, treating that water, and then pumping it out to your distribution network. And generally, the split between that service water coming in and the distribution going out and the pumping, most of that energy is using that distribution pumping because of higher head requirements to fill towers, maintain pressure in a distributed network. So we'll look at a couple of different options here. The big thing to understand before you go to look for VFD applications at pumps is what kind of condition are those pumps operating under. There's two general conditions: a low static head, which we typically find for like HVAC type pumps, may be applicable to surface water pumps that are drawing off of a lake or a river. And then there's high static head pumps, which are typically your high service pumps that are producing pressure for your distribution system. Usually applies to groundwater pumps that are drawing up out of a well. If you can see on these charts here, the blue line is indicating the system curve. So if you've got low static head, you're going to be starting off at the bottom of the chart. As you ramp up speed flowing through the pipe, you increase friction, which increases the head pressure in that system. Most of us are pretty familiar with how that works, but where that crosses the pumping curve is where your operating point is for the system. Where this comes into play with VFDs is as you slow down that pump, for a low static head condition, you can maintain the pump's operating efficiency for much longer. As you can see in the chart here, the efficiency curves kind of line up with that system curve for most of that operating range. So you maintain peak efficiency, even though you're slowing the pump down, as long as you've got a well-designed pump system. For high static head, though, you can see the head pressure's up here in the middle of the chart on the right. And so efficiency drops off really quickly. You also quickly get into a range where minor changes in head pressure create large changes in your output flow rate from a pump. And so you get into a region where you start to lose control with a VFD, where small changes in a control parameter make large changes in your system that can cause issues. So understanding what type of pumping system you've got before you start looking at a VFD application can help you determine upfront whether it's going to be beneficial for you or not. And what we tend to find is that for well pumps and surface water pumps drawing in, there's generally a good VFD application there. For high service pumps pushing out into the distribution network, there's sometimes a VFD application there, but it can be a little bit more difficult to apply VFD in a cost-effective manner. Usually, we find that situation is most effective when those pumps have been oversized for future growth of the community. The VFD can help compensate for that oversizing of those systems. So looking at well pumps, for those of you that have groundwater source water, if you're looking at VFD applications, again, that high head pressure versus low head pressure is going to impact a little bit whether a VFD is going to be a cost-effective option for you. But in general, we find that a VFD is effective for these pumps. Sometimes it might require a pump upgrade to optimize that VFD. But some of the benefits that you get when you add a VFD to a well pump and you slow down how quickly it's drawing water out of the ground, you reduce how much drawdown happens around the pump, which is shown on the image on the right here. As you draw water out of the groundwater, it has to flow in from the surrounding area. So you get a localized area where that water level is drawn down. That increases the amount of head pressure the pump has to generate because it doesn't have the assisting pressure of water sitting above the pump inlet now. So putting a VFD on this can help reduce that drawdown and actually reduces the overall amount of energy that a well pump will need to draw just to pull water up out of the well system. Where with a typical on-off control, you're going to get that high drawdown relatively quickly. So your pump's going to increase its overall energy demand while it's in operation and then cycle off. And then when it cycles back on, it quickly achieves that drawdown head pressure again. VFD can help mitigate that. Typically, we see somewhere around 9 to 10% savings on pumps that have been throttled back to reduce how much flow they send into the process system. But if your pump isn't properly selected or designed for application with a VFD, it is a potential here to see an increase in energy consumption by applying a VFD. Because as I noted in the high service head chart, the pump's efficiency drops off as the pump's flow rate is reduced, as pump speed is reduced. And so in some instances, particularly where your system curve is slightly to the left of the best efficiency point of your pump, usually most designs for consistent application tend to have that design where the system curve crosses just slightly to the left of the best efficiency point. And then in actual operation, usually the pump system curve shifts a little bit to the right and actually hits that best efficiency point. But as time goes on, corrosion starts to build up in pipes. You start getting filter clogging in the bottom of the well. It starts to move back to the left. And then when you try to put a VFD on there, you start to lose efficiency right away, and that can increase your energy consumption. So it's very important to understand the interaction between your system and the pump that's applied to that system to see if a VFD is going to be cost effective for you. In a case study that was done in the University of Wisconsin, they actually looked at ways to try to identify, what's going to be the most cost-effective application for VFDs. Can we predict that before we start trying to apply VFDs to systems? So they did a study of about 22 well pumps. They plotted the energy intensity of the pumps versus the flow rate. So how much energy per million gallons pumped are those pumps consuming? And plotted that on the chart. You can see here on the right, what you're looking for is that low point on the curve, where you're going to minimize the amount of energy you're using for every gallon of water pumped. For their particular situation, 9 out of their 22 sites were cost effective for VFD savings. To make those the most cost effective, simple payback for the most cost effective projects tended to be less than 10 years. Longer term projects, it tended to start running into issues with maintenance and things like that that would detract from the energy savings. And then again, as I noted earlier, when looking at the pump's best efficiency point, where its most efficient operation is on the pump curve, and where the system curve crosses over. Again, if that best efficiency or that operating point was just to the right of the best efficiency point, as the pump slowed down, you actually saw a slight increase in energy as speed was reduced before it starts tapering off again. And those were the pumps that had the most efficiency. And part of CDAC's assessment, if we come out to your site, we can try to get the pump curves for your system. We can do a quick analysis to figure out an estimate of what your system curve is, and we can help you figure out whether a VFD is going to be applicable to your system or not. On distribution systems, VFDs can be beneficial here, but a lot of times it's tied to operational strategies in your distribution network. If you can reduce the output pressure in your network, particularly during times of day when demand is lower, you don't need as high a pressure in the distribution network. You can reduce the pressure coming from your high service system, reduce the water level in storage water towers. There's a couple different strategies that can be employed to reduce the overall pressure during periods of low demand. This has a couple of different benefits. One, by reducing that required head pressure, you reduce the amount of energy that a pump needs to impart to the water to lift it up and fill a storage tower or to maintain pressure in your distribution network. But also, leaks in your distribution network are tied to that pressure. There's a minimum amount of pressure that must be maintained to make sure you don't have water leaking back into your potable water systems and causing contamination. But if you can get as close to that minimum as possible, you can reduce the amount of energy during certain periods of the day when you've got lower demand, and then you can ramp that back up for higher demand periods, typically early morning and 5, 6 p.m. in the evening when people tend to start doing cooking, taking showers, things like that. Something that can help with VFDs as well, when looking at on-off operation of pumps, when the pump kicks on at full speed, you get a slug of water pressure moving through your system. And that transient pressure, if it hits a bend in a pipe or a valve or fixture, it causes vibrations, and that can cause pipe ruptures, it can cause seal failures, and gradually over time it causes wear and tear on the piping system that will increase the risk of water main breaks and things like that. So even if you can't modulate the pressure with a VFD on the system, the ability of that VFD to ramp the pump up and down in speed and reduce that pressure transient in your system and reduce the amount of pressure that's going in that slug of water flow can reduce that risk of rupture and failure in pipes. Generally, what we find is if your water system is maintaining pressure through a water tower, unless you've got excess storage capacity, like a groundwater storage tank or multiple water towers, there's generally minimal energy savings that can be obtained there because you do have to maintain a certain amount of water volume in storage for emergency situations like a fire, so fire crews can hook up the hydrants and have adequate water to serve the system. But if you have storage capacity in your system where you've got that emergency storage capacity handled, or if you've got distribution pumps that maintain pressure instead of maintaining it through gravity feed from a tower, it's a lot easier to implement VFD control strategies and pressure control strategies to get more savings. But it does rely on that ability to have some kind of water storage to handle emergency situations and things like that. So again, we can look at your distribution system and try to help identify, is there an opportunity for reducing pressure and applying a VFD to the system and optimizing that pressure to reduce leaks and reduce your pumping energy. Somewhere else that we see VFDs have a lot of potential as far as percentage of savings is in transfer pumps and backwash pumps. These tend to be low head systems, so there's a lot of opportunities for slowing motors down and adjusting flow rates over time. But the initial energy savings opportunity from these is a little bit lower. These pumps tend to not have as extensive operating hours. They may run a few hours per day instead of 18 to 20 hours per day like your low service and high service pumps do. So there's a much greater percentage energy savings opportunity here, which if you have demand costs for your plant may be beneficial for you. But if you don't have demand charges on your plant, or the energy run times of these pumps is pretty low, this may not be a VFD opportunity for you, but it's something to look into. So looking at, modulating the backwash flow for your filters. Do you need to have full pressure for a filter backwash? Or is it, just enough to break the filter materials up and flush out materials? The duration of backwash is something we'll get into in the future. But transfer pumps, something that typically larger plants have, not really seen a lot in smaller plants. You might have a lift station lifting backwash water into a sewer main. But for larger plants that might discharge sludge to a lagoon facility or something like that, there may be a VFD opportunity there. Run the pumps at a slower speed, draining out backwash instead of running it at a high rate and cycling on and off. That could be beneficial for you. I just want to check the Q&A real quick here. I've seen a couple of notes come in. So we have a couple of engineers in the audience offering some helpful tips for VFDs. The first note, before we move on to our next section, VFD applications have benefits, but again, as we've been noting here, not in every situation. Understanding how affinities laws work for pumps, which is talking about for pumping energy, for each percent reduction in speed. If you cube that, that's the reduction in power you see for a pump. But if you square that, that's the reduction in head pressure that you see. And so for pumps with that high head pressure situation, since you're reducing the speed of the pump, you're also reducing its output head pressure. That puts a limitation on how slow that pump can operate, and that limits the energy savings potential. So very important to understand that, and see that can help you analyze that in a report. Something else that was noted in the Q&A, multiple pump installations start pumping, have smart pumping programming controls. Looking at automation for plants and tying in VFDs to an automation system, especially where you've got multiple pumps that stage to meet different demand levels. It's a good opportunity there for VFDs and optimizing operation of pumps. A lot of times what we see is to meet flow rates, you can run multiple pumps at lower speed with VFDs applied to them and get some energy savings that way instead of running one pump at higher speed. And so that's a good opportunity if you've got multiple pumps that work together in stages to save energy with a VFD. And one other thing to note, system pressure is a function of demand from end users, plus the requirement from National Fire Underwriters, and also Department of Public Health. You have to maintain a certain pressure level to make sure you don't have water coming back into your system and contaminating your clean water in your distribution network. So there's a lot of interaction here between different regulatory groups. But if you meet those minimum pressure requirements, what we're going to be looking for VFD savings is, are you operating as low as you can so that your energy intensity is as low as possible for each gallon of water that you pump? And that's where VFDs can kind of help, especially again, since a lot of plants are oversized for future population growth and expansion of their networks. At the current operations, a VFD can help match the installed capacity of pumping to the demand in your system. So some good comments there on VFD opportunities. Thank you. Next thing we want to look at is, since so much energy is tied into pumping water at plants, if you can look at minimizing the amount of wastewater you produce in your system, you're going to reduce how much pumping energy is associated with that water waste. So in distribution network control, we noted this earlier, if you can apply a VFD to your distribution network and reduce that distribution pressure as much as you're allowed to, and still meet regulatory requirements, you reduce on-off cycles, you reduce transient pressures that go through the piping network and can cause ruptures and damage in the system over time. These are all things that exacerbate leakage in your distribution network. And so if you can minimize those by applying a VFD, Each PSI of pressure you drop is going to reduce the amount of leakage that comes out of cracks and line leaks and things in the system. And if you can minimize those pressure transients, you're minimizing the risk of causing new leaks and ruptures in your system. Something else to look at is, again, if you've got storage capacity in multiple storage towers and maybe some ground storage tanks, you can look at during low demand periods in the middle of the day or late at night, does the tower have to be full then and maintain peak pressure in your system? Or can you let it coast down a little bit for a few hours in the middle of the day, a few hours overnight, reduce your amount of leakage that you have in your system during those particular times of day, and then fill the tower back up during your peak demand periods or just before those periods by ramping up your pump slowly to refill that tower and meet those peak demands. These are going to cut how much non-revenue water losses you have from leaks in your system. So it's going to save that water that you paid chemicals for, you've paid energy for to pump it, and it's going to reduce the overall energy that you apply at your plant as well. And so one more Q&A that's kind of come in here is talking about specific energy. I may, at the end of the presentation, if you're willing, please, I'll let you speak. Just raise your hand in the chat when we get to the end of the presentation. I'll let you talk about that a little bit more in detail. But something else to look at for minimizing water waste is your backwash controls. A lot of the wastewater systems CDAC has looked at in our past program year employ gravity sand filters or pressurized vessel sand filters. And the way they do backwash to those systems is they reverse the flow of water through that system. That helps break up sand particles, buildup of materials in that sand bed. And then they'll also do an air scour as part of that in a staged process. So usually air scour happens, breaks up some of the materials on the surface, and then backwash water goes through the system, flushes out those broken up materials into the backwash line of the filtration system. This process can be automated. You can add sensors to your backwash system to minimize the amount of time that the backwash is operating and thus cut down on how much backwash water occurs. Differential pressure sensors or turbidity sensors across the filter can help reduce backwash by, instead of doing it on a scheduled rate, you can do it based on differential pressure across the filter or outflow turbidity from that filter system, looking at solids content and pollutants that might be coming through the filter. As it builds up over time, you get an initial increase in filtration capacity as more materials start blocking the passage of particulates through the filter. But eventually, as it gets loaded, you start getting breakthroughs. Some materials get forced through by the pressure, and you start seeing an increase again in that turbidity. And that's when you want to start, a sensor would trigger a backwash cycle for a system. So there's a couple different ways to look at how to control backwash water, minimize the consumption of water during the backwash process, and minimize how many times per day you're doing a backwash cycle. Noting here in a case study, Columbus, Georgia did some upgrades to their old gravity media filters, added some controls, and saw a 50% reduction in that backwash water consumption. Something else to look at on the energy side is scheduling of backwash for off-peak times of the day. If you can add a little automation to the system, instead of allowing a backwash to happen during peak energy draws in the late afternoon, between 3 p.m., 6 p.m. in the afternoon and evening, if you can offset that backwash to a time when energy demand is lower, especially if you're on a time of use schedule, which is probably common for larger plants, maybe not so common for small plants, that can help save you some demand charges on your energy costs. We have seen in certain situations where you're kind of on that line between utility rate scales, if you can schedule those pumping demands for off-peak times, it can actually reduce your rate schedule and reduce some of your fees. So there's some potential savings there on just energy costs, if not overall energy consumption. Something else is just installing a backwash tank, some kind of storage that you can fill gradually over time, reduce the amount of pumping energy you put into the backwash instead of having an instantaneous demand for backwash flow at a design flow rate. You can store up some water in a tank over time. You have a lower pumping rate at a lower head pressure over time, and then run that from that storage tank back through your filtration system during a backwash cycle. That can save some energy on pumping and demand charges as well. And then some advanced technologies. A lot of the plants that we work with, 50, 60-year-old, they've been, sand filters that have been in place for decades. Maybe they're due for media replacements, things like that. Those are a good time to start looking at potential upgrades and new technologies for those filtration systems. So simultaneous air scour and water backwash is something that we found recently, where instead of doing a staged air scour and then a backwash cycle, you can do them at the same time. What this allows for is a lower flow rate of water through the sand bed to break up materials, because you're going to use air bubbles as well to break up those materials and flush out impurities. This allows a sub-fluidized flow rate for those sand filters, so it reduces the flow rate demand for backwash water, so you're reducing your pumping energy. And it breaks up those materials and flushes them out faster than a staged backwash and air scour type control system. So there's a case study on the next slide we'll look at, about a 50% reduction in backwash water, and reductions in makeup water pumping. A lot of times we see at plants, backwash flows come from the storage tanks, the water towers in their distribution network. They do some valving changes that pressure backfeeds through the pumps, but then they've got to pump raw water and their high service pumps to replace the water they use for the backwash. So they're essentially double pumping some water. And so there's some energy tied up there that can be saved by reducing backwash water consumption. And then there are newer filter technologies. The one shown on the screen here is a series of polymer plates that are pressed together. As particulates build up on them, backwash, back pressure builds up on that filtration, it automatically kicks into a rapid backwash cycle that only lasts a couple seconds. Those plates can separate once that pressure backs off of them, and then flush out materials very rapidly, much faster than a sand filtration system. Something to consider with these is they do have some limitations on particulate size they can filter. So maybe this is a pre-filter system that extends the life of your regular sand filters. But there's these technologies that are available out there that are starting to permeate into the market that, particularly for older plants that are looking at filter replacements for entire systems or filter media replacements. Maybe it's time to also look at, is there a way to extend the life of those so you reduce your long-term costs by adding in a pre-filter system or a new type of filtration control technology. So a couple things that come in the chat here in the Q&A, just touch on those before we move on to our next discussion topic. Okay, just some comments from some friendly people in the chat that have worked with us before. We'll let some of those people talk here at the end. They've got a lot of great ideas. But again, focusing on a lot of plant energy is tied up in pumping. So if we can reduce that pumping energy, how much water we're moving, we're going to see savings. Distribution networks are kind of the, it's buried under the ground, it's out of sight, out of mind. So when leaks happen, we don't necessarily know they're there. A few gallons per minute can be thousands of gallons a month, tens of thousand gallons per year. So implementing leak detection into either a line item in a city's budget to do periodic leak detection with handheld sensors, or implementing sensors on what we're showing on screen here is something that can be tied into fire hydrants, and it tests for leaks between each fire hydrant. So there's some ways to automate this process to free up some labor time. I know a lot of smaller communities, your water operator is also your wastewater operator, is also your guy that patches the roads, is also the guy that fixes down power lines. So they wear multiple hats in the community. Their time is precious. Anything you can do with some automation technologies to help improve their effectiveness, where they can target major issues before they become a problem, is going to be beneficial for your overall system. Leak detection is one of those automations that can be set up in your community. So you're going to reduce that non-revenue water loss. You're going to reduce the pumping energy required at the plant to make up the water that you're losing. You're also saving on the treatment chemicals for treating that raw water and getting it cleaned and purified. You're going to reduce that risk of contamination. A line break in one part of the system can cause a pressure drop in another part that allows contaminants to come into the system there. And then you got boil water advisories. We all know how much water operators hate those boil water advisories. So the national average for non-revenue water loss is about 22%. A lot of that is water main leaks. Some of it is unmetered water usage. Fire hydrant usage sometimes falls under that category. But about 75% of that in a national study was found to be preventable and recoverable through fixing line leaks, through monitoring water consumption. But if you can set up these networks of sensors, or if you can get a regularly scheduled and funded testing program for your water network, you can help ensure that you're not going to have a surprise water main failure or something that's going to cause an issue for your community. And in the end, cost a lot more overall. So an example here, Connellsville, Pennsylvania, they implemented a line item budget that every year they do some testing and some repairs on their system. And you can see here how much they've reduced their water losses over time. So they installed some acoustic leak detectors. They cut their non-revenue water loss from 25% to less than 12%. So they went from slightly above the national average to 10% below it in just 6 months. So a really good example here. In Southern California, Edison was another program. They partnered with some water utilities to do some testing, things like that. So they had a program that helped fund water programs, because that helped the utilities save on electric energy, reducing that pumping energy associated with those water losses. And so again, an 18-month program, $300,000 in savings across multiple water utilities. And then just some miscellaneous things that we see in a lot of plants is some energy savings opportunities. One of the big ones we see is almost every plant we go to, you've got bare metal pipe with 55-degree water in it. And in the summertime, if you don't dehumidify the air in that space, you get condensation on that piping that drips off, causes slip hazards on the floor, causes corrosion concerns for the piping and materials under the piping that water might drip on. And so we see a lot of dehumidification in place in buildings. And one of the ways you can mitigate that energy use is by insulating that piping. You can see an application here of a spray-on insulation coat that can have some maintenance implications, as far as now you've got, if you replace a section of piping, you've got to contact them again to reinstall this spray-on insulating material. But there are fiberglass wraps available and things like that. But we have yet to been to a plant in Illinois that has insulation on their piping system. Part of that is you get some free cooling in the summertime. You got 55-degree water running through pipes through this building all the time. Outside of the condensation issues, it's free cooling for the building, so you're saving on HVAC energy. But if you can add a little bit of insulation to that piping, just enough to prevent the condensation on that surface, there's so much water moving through these pipes, so much surface area of piping, you're still going to see some cooling. You could get that surface temperature of that pipe up to 60, 65 degrees. You're going to prevent a lot of that condensation risk. But you're still going to have the cooling effect of that surface being cooler than the air around it. So there's an energy savings potential there. And also some benefits as far as protecting your pipe galleries from corrosion and water damage and slip hazards, things like that. Something else is using advanced HVAC technologies. So here we're looking at water source heat pumps. We've been seeing these grow in wastewater facilities. But we haven't yet really seen these applied in water facilities. But you're pulling ground temperature water at 55 degrees, passing it through a building. It's going to be about that same temperature for groundwater sources throughout the year. If you're pulling surface water, it's going to vary a bit more. But in general, you're going to have the ability to get heating and cooling out of that water coming through your plant. So before it hits your treatment process, you tap into that, run it through a heat pump system. Once it's gone through that heat pump system, you dump it back into your system and then run it through your treatment process. And you've got low cost, high efficiency heating and cooling, where, for gas systems, you're looking at somewhere between, for older systems, about 75% efficiency. For newer systems that are standard efficiency, are about 80-85% efficiency. And then if you've got condensing systems, you're at 90% efficiency. If you can put a heat pump on there, it's somewhere between 250-300% efficiency on the electric side. Electrification can also help with meeting net zero goals in the future. If you're taking away that combustion equipment, now you can take that electric heat pump and put it on solar or wind or some other renewable electric source. And that can help if your community has goals for reaching net zero in the future, or just reducing your overall carbon footprint. That's a big step in that direction, is getting away from combustion appliances and moving towards electric heat pump technologies. And so that brings us to the end here. We did have, there's an anonymous attendee that wanted to talk about specific energy. If you raise your hand in the chat, I'll let you talk about that real quick. So I think you probably have some insights there that you can share with us. And if there are any questions at all about what we've covered, please throw that into the Q&A. Let's see here. Zia.
Yeah, I just wanted to mention, while we're waiting for that attendee to raise their hand so we can let them speak. Just wanted to mention, I put in the chat, you were talking about net zero, Sean, and one of the great opportunities is that the Illinois Clean Energy Community Foundation provides funding to plants who commit to going net zero energy use, and can provide funding to help get you there. So some of the things that Sean mentioned, there's that unique funding opportunity, and I put that in the chat. Also wanted to mention that a couple other things. One, that please check as you're doing these upgrades with your local utilities to see what sorts of incentives are available. If you ever have any questions about navigating incentives or want help with funding applications, please feel free to reach out. We can help direct you to whomever your local utility is to get support. Ooh, and I do see we have a hand raised. All right, Robert, would you please unmute? I think Sean's going to unmute you or let you speak, and please ask your question.
Yes, actually, this is more of a statement. I represent the heat and frost insulators, and Sean, with what you talked about with mechanical insulation on the piping systems, you made a great point of spray insulation being an application to reduce condensation. And the point that you made that the maintenance, the regular maintenance of removing that pipe and having to have somebody come back and re-insulate that pipe with that spray insulation. We represent. We don't do that as a craft. We do fiberglass insulation. We find that the maintenance of that is much easier for the plant operator and upkeep on maintenance. We've also done some audits ourselves, and we've noticed that insulation, uninsulated pipe in a gas system, if you actually put 1 inch insulation, a 1 inch of insulation on an uninsulated pipe, you could reduce those BTUs by up to 90%. If there's any people that have any questions about that, I can always talk to the plant operators with that, or with CDAC itself.
Yeah, that's a great point. Actually, I didn't cover the heating benefit of insulating the piping, since that's 55-degree water that you're constantly fighting to heat up. Your gas system's trying to heat your building and heat the water flowing through it that's constantly being replaced. So a little bit of insulation can really go a long way to help mitigate that energy. Thank you.
Thanks, Sean.
Great. And if anybody else has questions, please put them. That was a great point. Thank you so much, Robert. And if anybody else has any questions or would like to either put them in the chat or raise your hand, we can certainly get you up here and you can ask your question live. We have some great experts in the room too, so I'm thankful for those also who can contribute and add to our presentation as well.
Well, it looks like the person who was going to talk about specific energy earlier has jumped off, had to go to another meeting. But specific energy is essentially how many kilowatts are you using per gallon of water that you're pumping. So it takes into account the efficiency of the motor on the pump, the efficiency of the pump itself. If you've got a VFD applied to it, the efficiency of that. And so as you adjust the speed of a pump, you adjust the pump's efficiency in relation to the system curve for your distribution network or your well water system. And so that specific energy will change over time. Generally, the more you slow down the pump, in most design conditions where that design point of operation is slightly to the left of the best efficiency point, your specific energy tends to increase over time. When you have that slightly to the right of that best efficiency point as a design option, you see a slight increase in that specific energy, so you reduce your total energy demand, and then it will start to increase again as you get lower in speed. And usually that's where you want to program into the VFD kind of a cutoff, so you're not increasing your energy consumption again.
That's great. Thank you, Sean. Let's see. So the recording slides and the video will be available. We will send them to you once they are live on YouTube and on our website. So stay tuned for that. And thank you for that question. And please feel free to share this with other members of your team or others within your network that weren't here today. We always want to spread the word about efficiency opportunities. So please feel free to share it widely.
We did have one question come in about data collection that's required. So we collect 2 years of utility data. If you're on ComEd or Ameren, all you've got to do is send us one bill. We can go to the utility, get the rest of that information ourselves. If you're on a co-op, you'll have to get us all that information. We may only request a year if that's all you've got that's easily available, but we tend to like to get 2 years of data. That way, if there's some emergency situation that happened that caused an energy spike or an energy drop, we can account for abnormal situations by looking at a more normal time of operation. We also try to get a flow diagram for your plant system that's going to show us what treatment systems you have in there, what pumping systems are applied to the system, just so we have an overview of what we're getting into when we come out to the site visit. And then we'll, in our initial conversations with you, we'll get some information about, do you know pump horsepowers, things like that. Just some general equipment ideas. But most everything else we will get when we come out on site. We're going to take pictures of nameplates for pump horsepower and pump systems themselves. We'll get pictures of lighting and HVAC systems and other factors that are going to impact your energy. So really that big upfront is the utility information.
Another piece that Sean didn't mention is we do ask for monthly flow data. So it can either be in the form of your MORs, or if you have a spreadsheet that just lists the month and then the flow that month, that is what we will ask too, because we do some benchmarking to understand your energy usage based on how much you pump and how much your flow is. So that is also a piece of data. And one thing on the utility data we understand can be totally challenging to get. And we'll work with you to figure out how we can best support those efforts. Sometimes we work with the city or municipal clerk or whomever manages those bills to get that information with you. You don't have to do it all yourself. And we'll try to find ways to make it as simple as we can for you. But like I said, that's the lift on your part. We'll do the rest.
Okay, well, I don't see any other questions in the chat or Q&A. If you do think of a question after this presentation, Our contact information is there on the screen. Feel free to reach out to us. We'll be happy to talk with you and answer any questions you may have. I want to thank you all for joining us today. It's been great talking with you. Hope you have a wonderful afternoon.
Bye. Thank you so much.